Hi everyone. Thank you so much for joining us today on our ML mathematics session. We have with us a very special guest speaker, Kelvin Yu. Kelvin is a PhD student at Brown University, advised by Professor Chen Sun. Prior to this, he was an AI resident at Google Brain in Mountain View. This session is based on his paper, Understanding Diffusion Models, a Unified Perspective. Thank you so much for your time, and I'll hand it over to you.
Yeah, thank you so much for having me. I'm pretty excited to talk to you all, I guess, about diffusion models today. Let me quickly share my screen. Great. Yeah, so today's talk is about, I guess it's kind of a video companion to the tutorial, Understanding Diffusion Models, the Unified Perspective. I was told that this is kind of like a math group. Like I've generally found that like math on slides are kind of hard, at least for me to follow. And I think I'm leveraging the fact that a lot of the math has already been written out, I guess, in very clear lines and derivations in the tutorial. So the way I approach this talk is actually more focused on visualizations and intuition, like a visual format. Hopefully maybe is like a companion to like the proofs. If you're very interested in the math and the proofs, you can go through the tutorial. If you're still stuck on something, you can always write me. Yeah, I didn't put too many like derivations and equations in this talk. And yeah, please interrupt with any questions. Yes, JY, what's up? Okay, anyway. Okay, yeah, thank you for the introduction. I guess I don't need to introduce myself. And I guess also before I dive in, I think acknowledgements are definitely in order. Like I kind of wrote this tutorial from my understanding of diffusion models, and I had to like go and learn quite a lot. And in doing so, I referenced a lot of existing work from many different amazing people, and they have like great blogs, tutorials, papers themselves. So please like check them out and reference them. I'd say that like for the tutorials, theory and proofs, a lot of it was based off existing stuff from Lily and Wang, and internally, Josh also wrote, also inspired from Lily and Wang, some derivations that were very helpful. They kind of shaped the derivations and proofs that you see in the final tutorial. I actually learned about Tweedy's formula and connecting interpretations across diffusion modeling and score-based generative modeling from Ben Poole. He gets like full credit for that. Score-based generative modeling, of course, on the blog posts, papers, and talks with Yang Song. And for guidance, like Sandra Dielman's blog posts, Jonathan Ho's papers are fantastic. And I definitely want to thank Jonathan Ho, Dirk Kingma, Ben Poole, Yang Song, Jing Chen for thoroughly reviewing draft tutorial. They spent a lot of time on it, providing feedback. And I think I should also thank my mentors at the time in the Brain Applied Research team, Xiaohui Yu and Siri Wang, for supporting me in writing this. So let's talk about diffusion models. I think this talk will be maybe a bit long, but hopefully very comprehensive. And we can start with a major takeaway, which is that diffusion models, they're really great at generating samples from conditional distributions, and we'll start working towards, how we can get those samples, conditional samples, p of x, y, for very interesting cases, right? So the first, use case that you might see as a motivating example would be like class condition generation, where here we're trying to generate, images conditioned on a class label. We can, successfully learn a diffusion model that can take in a class label and learn a distribution of images corresponding to that class label, and we can generate samples for like, let's say, goldfish or blue birds. Maybe another use case that many of you have likely seen is text-to-image generation, where here, like the p of x given y is probability of image given a text caption. So here we want to provide a text caption, right? A painting of a fox sitting in a field of sunrise in the style of Claude Monet. We want to be able to generate images that are aligned or respect this text prompt. And diffusion models have been fantastic at that. And maybe another use case is like super resolution, where you can take a low-res image, condition on it to generate a higher res image. And here we can actually showcase cascaded diffusion models, which hints at something more powerful, which is we can also, chain together multiple separately learned diffusion models to form a pipeline that can take maybe a class ID up to a really high resolution image. You can chain together individual diffusion models that can take the class ID, the class condition generative model to produce a low res image, conditional low res to make a high res one, and maybe even more high res one. So diffusion models are quite flexible. You can learn all sorts of fancy condition distributions and even chain them together for a nice final outputs. So I guess I want to take some time to quickly recap generative modeling. And the way that I like to think of generative modeling is, to summarize it, we want to learn a model of a distribution from which we can generate new samples, hence generative modeling. If we try to write it out into explicit lines, right, the modeling portion is we're given, let's say, some samples from a true data distribution. Maybe it's very complex, and therefore we want to model that true distribution with an approximate one that's parameterized by learnable parameters theta. So we want to learn piece of theta of x that's approximately equal to p of x. That's the modeling portion. And after we've modeled something well, we also want to generate new samples from this approximate distribution, hopefully in a very cheap way, using our approximate model, and that's a generation step, generative modeling. So it's always tied with modeling and sampling. And what are some common themes of generative modeling? Well, we want to learn some complex distribution, piece of theta of x approximates p of x, but we prefer to work with simple distributions such as Gaussians. Particularly Gaussians are nice because we can compute their likelihoods. We can generate samples really cheaply and efficiently. We can integrate over them. We know all their properties. So we like working with simple distributions like Gaussians, but we want to learn to model and sample from some complex distribution. So a very common idea that you might have seen is, well, let's just learn a complex function, for example, a neural network that transforms a simple distribution sample, like a Gaussian, into a complex one. So like this, I think you might see this this pattern over and over, specifically or particularly in image-based modeling, where you want to convert maybe a Gaussian sample or a Gaussian distribution through some flexible neural network into a data sample or data distribution. You might have seen this before in VAEs, where after we learn this encoder-decoder structure, we learn this probabilistic encoder. After training, we can throw it out, and because we've trained that probabilistic encoder to be similar to a standard normal, during sampling time, we could actually just sample from the standard normal, use the learned decoder to generate a data sample. That's one way to convert a Gaussian data sample to a complex data sample. And you might have seen this in GANs as well. In GANs, we explicitly take a Gaussian standard normal vector, pass through the generated network, and it outputs a sample from the complex data distribution. You've also seen this in normalizing flows, where you try to map the Gaussian distribution into the complex one in a reversible way, and you'll once again see this here in diffusion models. So the observation that we make, the high-level intuition behind diffusion modeling, is that if we just, let's say, take images, we take one clean image, and if we add steady amounts of Gaussian noise to this image, we repeatedly sample a Gaussian noise vector and apply it, sample another one and apply it, eventually it'll corrupt this image into something that's indistinguishable from a random standard Gaussian sample. So visually, it's we show a clean image, we add one sample of Gaussian vector, we get a corrupted one. Now we take it again, the one that we just corrupted, we add another step of Gaussian corruption, and it becomes even more noisy. And over many steps, if we do this in a steady procedure, it takes a clean image and turns it into something that's indistinguishable from a random Gaussian sample. We've corrupted all the structure in the image. And keep in mind that just this corruption process, there's no learnable parameters, right? We don't need to learn anything. We just repeatedly sample something and apply it maybe with some scale. It's very easy to destroy structure, destroy an image. Well, noticing that this is one way to go from a clean data sample to pure noise, or something indistinguishable from pure noise, diffusion model is simply trying to learn to reverse this procedure over many time steps. And if you can efficiently learn a way to reverse this procedure, then you've found a way to take something indistinguishable from a standard Gaussian noise vector and steadily denoise it into a clean data sample. So that's the goal of diffusion. So to take a step back and build into what we're actually modeling, we can start with the VAE. And visually, we often see a VAE as the following. We have this probabilistic encoder and probabilistic decoder. And for the latent space Z, we try to match it along with the standard normal. And the clever thing about VAEs is really figuring out how we can perform backpropagation through samples. Because sampling by nature is a very non-differentiable procedure. But it turns out that if we model the probabilistic encoder as a Gaussian, in other words, if we're predicting a mean and standard deviation sigma, and we're parameterizing this, and we want to update this. If it's a Gaussian, then we can actually perform backpropagation through the reparameterization trick. And I want to spend time recapping the reparameterization trick because it's something that we will apply over and over in diffusion modeling and in the course of this talk. So reparameterization trick basically says that a complex or arbitrarily parameterized Gaussian with arbitrary mean and arbitrary variance sigma squared, we can actually generate samples from it, leveraging samples from just a standard normal with no learnable parameters, just like zero mean, identity covariance. And how it does that is, we can take samples from the standard normal. We can actually scale it by the standard deviation of this arbitrary parameterized Gaussian. So for any arbitrary parameterized Gaussian, we take the standard deviation, scale it, and we can also shift it with the arbitrary parameterized mean. And in essence, what we found a way is to rewrite the sampling procedure for arbitrary parameterized Gaussian in terms of its components, which we can now backprop through, because the sampling portion, the non-differentiable portion, now no longer has any parameters. It's just we're sampling from the standard norm. So all these X samples can be rewritten as samples like epsilon samples. So we will apply the reparameterization trick over and over. And so visually, we often see a VAE as this bow tie-like figure, the encoder and the decoder. But you might also have seen it in terms of these circles and arrows, where the circles kind of represent I guess spaces, and then the arrows kind of represent transitions where you can learn an encoding transition v of z given x and a decoding transition v of x given z. We can curve the arrows just for visual beauty, and we can even collapse it back into itself, just to basically say that we're learning an encoder that takes something from X to Z space, to the latent Z space, something from the latent Z space back to X space. And I guess this is just some visual notation, it's really trying to describe the same thing. Well, what's the intuition behind what is learned once we have latent variable? Well, recall that in modeling, we're trying to learn piece of theta of x approximate to the true distribution v of x. And if we assume that latent variables z exists, usually they're of a lower dimension. We can think of this as compressing the data x into some lower dimensionality z. And hopefully once we compress, we are hopefully is learning to also compress it in some sort of learned semantically meaningful structure. And if this is true, then we can also perform some sort of controllable generation, or maybe we can manipulate some of the bits or the values of the latent variable and decode back into an image that has changed in a way that we like. Yeah, Sunny.
Calvin, in the reparameterization trick, do we have to go from standard normal to an arbitrary Gaussian or the other way around? And why do we do that?
Oh, yes. So in a VAE, okay, so in a VAE, we want to learn a complex or an arbitrary parameter. We want to learn distribution over Z, right? And usually we learn that by outputting, some Gaussian parameterizations like predicted mean, predicted covariance. But how we learn that is jointly. So we'll learn a distribution over Z, then we'll, you know, decode Z back into X and try to learn, you know, it to match the original input. But when you backprop, you cannot easily backprop through the predicted mu and sigma from this encoder if you sample from it naively. And then if you cannot backprop through it, then you cannot update mu and sigma to become better predicted you know, distribution parameters. And the way around it is the reparameterization trick, because instead of just sampling from that distribution directly, we actually now sample from a standard normal, which has no parameters, and then manipulate the standard normal sample into a sample that's equivalent to one that was sampled from the complex distribution. And that's the reparameterization trick. And now when you backprop through, you know, operations that involve X, you won't need to have any gradient updates for epsilon because there were no parameters there. And that's nice because that's where all the sampling nastiness and non-differentiability like occurred. But you can still backprop with respect to sigma and mu to actually like learn those parameters.
Sure. Yeah. It does. Thank you so much.
Yep. Okay. So yeah, we generally assume in like VAEs that, you know, Z is lower dimension, and hopefully we want, like, we would like to learn some compression, semantically meaningful structure, controllable generation. We can model the joint distribution of data and latents as follows, and, you know, maximize like the evidence lower bound, etc. But we won't be doing the derivations or proofs here. You can refer to like the written tutorial for like, you know, line by line derivations. But for VAE, it turns out we can generalize this, enabling a hierarchy of latents. Like the question is, well, why restrict ourselves to a latent dimension? Maybe there's a hierarchy of latents, and maybe that makes sense to model. So we can have, let's say, T hierarchies of latents. And if we try to learn a hierarchical VAE, a generalization of VAE, essentially learning a bunch of stacked VAEs, where now maybe the Z1 can be decoded from a Z2, encoded, etc. And here I've just shown kind of like the Markovian hierarchical VAE. You can think of this as a generalization of a VAE. And a big question is, well, in a VAE, we learn two networks. We learn an encoder and a decoder. Well, how many do we need to learn for a hierarchical VAE with, let's say, like T latents, or like T latent hierarchies? Well, naively, each of these encoders on the bottom, each of the decoders on the top, those black arrows, require their own model. So in the most naive situation, we would learn T encoders and T decoders, so like 2T total neural networks, which can be quite prohibitively expensive. And so we can start making some simple assumptions to simplify this modeling. So the first thing is, well, what if we assume that all the latent dimensions are the same? Like the dimensionalities are the same. We're no longer like compressing and compressing and compressing. What if we just compress in this first encoder and then maintain that dimensionality for the rest of the hierarchies? Well, if we make an assumption that all the latent dimensions are the same, we can also simplify the modeling of all these individual encoders. And we can simplify them by just having one encoder neural network. We can also simplify all the decoder neural networks, all these decoder transitions into one consistent decoder neural network. And we can leverage this because the dimensionality is the same, so we can reapply the same network over and over, right? It'll always expect, you know, an input of a particular dimensionality and output something of the same dimensionality, so you can like chain it. But we also need to provide in an index T that tells the encoder how it should behave, because the transitions are still different. That like how you encode different hierarchies are still different. So even though the input and output are the same, that enables us to reuse the network, we should still tell the network which hierarchy we're processing it for, right? So when we pass in Z2, or when we pass in Z1 to predict to encode to Z2, we should also tell it that it should be turning Z1 to Z2. So we pass in indexing to, I guess, change the encoder's behavior. But we can collapse all of these transitions into one encoder neural network. Similarly, we can collapse all of these decoder transitions into one neural network and just tell it how to change its behavior conditioned on this time index t. And we also need to learn an encoder that takes our data sample x and brings it to z, as well as a decoder that takes our predicted z, the final z, back into x. So if we make the assumption that all the latent dimensions are the same, then we can get away with just learning 4 neural networks. Does anyone have any questions on this? Okay, cool. Now, what if we make a further assumption that all the dimensions are the same? So this might be a bit strange, because if all the dimensions are the same, we're moving away from learning like a compressed latent space. Yeah. Come on.
Just a small question. Why do we refer to these as timestamps?
You can refer to them as hierarchies. For now, we can also, you can also think about the hierarchies as time. It's like, I guess it's just, it doesn't make that much of a difference how you refer to them. You can think of it as like steps, right? Like I encode 1 step, then 2 steps, and 3 steps, 2 steps. And you can think of steps as like time steps, or you could just think of them as hierarchies. Yeah, I guess the term is a bit flexible. I hope it's not too confusing. We're not actually operating in like time. It's just like a notion of time. Yeah. Okay. So if we make the assumption that all the dimensions are the same, then the first thing that we notice is we're moving away from like learning a compressed latent space. We're no longer thinking about like semantically meaningful structure for these z's, because we're maintaining the same dimensionality. And the second thing we can do is we can actually rewrite our notation a bit, because z no longer denotes something of a different dimensionality. We can rewrite everything in terms of x, because x has the same dimensionality. We can just provide different indices, like hierarchy indices or time indices or whatever you like. And now the transitions, we can update the notation as well to just say that we're going from, some xt to xt plus 1, or x to xt minus 1. But if we make the assumption that all the dimensions are the same, then for the encoder, now we can use one consistent encoder to model all of these individual transitions, provided we also provide time index that denotes which transition specifically we're modeling at any given time. And also one consistent decoder model that can handle all of these individual decodings indexed with like a time index or a hierarchy index. And keep in mind that just like a VAE, this is the hierarchical VAE, the encoders and decoders are all probabilistic neural networks, where actually they're not predicting directly xt plus 1 or xt minus 1. They're predicting Gaussian parameters mu and sigma, from which we can generate samples of xt plus 1 or xt minus 1 using the reparameterization trick. So that's actually how we go from xt to xt minus 1 in decoding. We predict Gaussian parameters and generate the xt minus 1 sample using reparameterization trick. Now, let's take another leap of faith and make another assumption. And the other assumption is, well, what if we assume that all the encoder transitions are known Gaussians that are centered around their previous input? And if these encoder transitions are known Gaussians, known in that we know their parameters, we don't need to learn them, well, that means that the encoder no longer is something that is needed, that we need to learn. If we make the assumption that all these encoder transitions are known Gaussians, so the input, then the only thing we need to model is a decoder neural network. And let's take a look at what making that assumption will give us. Making the assumption of like a Gaussian transition provides us with the following. We can take a look at one encoding at a time. So for x0, it's our clean data sample, right? And if we make the assumption that this is a Gaussian transition, because it's centered on its previous input, the mean is x0. And let's say that the standard deviation sigma 1 is something that we know and can set as a hyperparameter. It doesn't have to be learned, although you could. But let's just assume that it's known. This is a known Gaussian transition. Then that means that x1 looks like this. x1 can be thought of as a Gaussian corruption of the clean data image x0. Why? Because we can directly visualize a sample of it through the reparameterization trick. x1, if we write it in the representation trick, is equal to x0, which is its mean, plus sigma 1 times an epsilon noise vector, right? We call that the representation trick is mean plus standard deviation times a standard Gaussian sample. And so you can see that after undergoing this encoding, this Gaussian transition, it's really just adding some scale of Gaussian noise to this clean image. Well, what about the transition of x1 to x2? Well, this is also a known Gaussian encoding transition centered around x1 with some known standard deviation sigma 2. And this produces something that's even more noisy, something that's a noisy version of the clean image x. Because once again, we can visualize it using the representation trick, where we take the mean, which is now x1, noisified version of the clean data image. We add another Gaussian sample, right? And that's what x2 looks like. It's like another even more corrupted version of x. So these are just independent applications of the representation trick to sort of visualize what's going on. It turns out that you can take x1 and substitute it here into the equation that we use to generate x2. Oh, sorry, I jumped ahead of myself. So yeah, it turns out that like if we treat each of these independent encodings as Gaussian transitions centered around the previous input, we're just steadily adding scaled versions of Gaussian noise. Really, what we've done is mathematically modeled this Gaussian corruption process. This process that will iteratively take a clean data sample and bring it to something with enough time steps that is indistinguishable from a standard noise vector. So we've just basically modeled the Gaussian corruption process. So let's take a look at the transition from x1 to x2. Well, we can actually substitute in the x1 formulation, which is its own representation trick, and we get the following. We get that actually x2 is written as the clean image x0 plus sigma 1 times epsilon 0, right? That's x1 plus sigma 2 times epsilon 0. And we can actually aggregate this into one sample, because you can sum up Gaussians with their like known parameterizations and aggregate them into basically a sample from one Gaussian with a new scale, where the scale is the square root of their variances. So what we've actually done is we've collapsed multiple applications of the reprimerization trick to basically get a distribution of x2 conditioned directly on x0. The distribution of x2 is a normal centered around x0 with standard deviation alpha 2, which is written as a function of known sigma terms. And this is done using the reprimerization trick, because now we can take this reprimerization trick sample and make suggestions about what the overall data distribution looks like, which is this Gaussian. And we can do this again and again, and basically discover that if these are all individually known Gaussians, we can rewrite them as Gaussians that are all centered around x0. Like they all have mean of clean image x0, but just with different standard deviations alpha t. Right, so the distribution of each of these intermediate hierarchies is q of xt given x0. It's always a Gaussian for any arbitrary t, and it takes the form of mean x0 and alpha t squared I covariance, where all of these alphas are known or fixed. So we come back to making all these assumptions, and we can do a lot of simplifications. And this last simplification, all the encoder transitions, allows us to aggregate and simplify the distribution of each intermediate latent, right? And it turns out that actually, loosely, this is exactly what a diffusion model is. It is a hierarchical VAE, Markovian hierarchical VAE, with the following assumptions: that all the dimensions are the same, and that we have these encoder transitions with their known Gaussian center around the previous input. And implementation-wise, really, it's just a single neural network that we need to learn, which is this decoder. It's just one neural network. That is a probabilistic decoder. Takes an xt and t, predicts parameters such that we can generate samples xt minus 1. So a quick quiz is like, well, the data set that we're given is only clean images x0, right? Supposing we're trying to model images, but the decoder takes an xt as input. Well, how do we get our xt's to train on? Well, the answer is we get the xt's to train on by following these pink arrows. We know the distribution of xt given clean image, which is what we have as our data set. So for any arbitrary xt that we want to generate, we just take the clean image, add the respective amount of Gaussian noise corruption, and that is our xt. And that's what we train our decoder model to handle, which we will do in a supervised way, which we will soon see. So now we're interested in trying to optimize our decoder. We're trying to find out, how to output the best xt-1 given input xt's. So our denoising decoder looks as follows, right? We take an xt and t, pass it to the decoder, generate a sample of xt-1 given predicted mu decoder and sigma decoder due to the reparameterization trick, right? It's just a probabilistic decoder. So our prediction x-t-1, x hat t-1 is written the following way. But what is the form of xt-1, right? We want to try to formulate this as a supervised learning problem, so we need labels of xt-1, like some sort of ground truth label of xt-1 that will improve our predicted xt-1. Well, recall that when we derived the pink arrows, we know the distribution, the ground truth distribution of all these xt-1s, or for any arbitrary xt's t, right? And so we recall that the distribution for any arbitrary xt is given x0 is, a Gaussian center around the clean image with alpha t squared I covariance, which are known and fixed. So the ground truth form of the distribution of xt-1 given x0 says that true samples xt-1 can be rewritten using the reparameterization trick as x0, the mean, as alpha t-1 times epsilon, right? So now we try to formulate optimization of diffusion modeling as a supervised learning problem. The question is, our prediction is this equation on the top, and the ground truth of xt-1, the formulation that it really takes is here in the pink box. Do we really need to predict sigma decoder for this probabilistic decoder? Well, it turns out that we don't, because alpha t-1 is a known parameter. We don't need the model to predict something that we already know. We don't need it to learn it. We can just apply it directly. It's exposed to us. And what is the ground truth signal for mu decoder? Well, the ground truth form of xt-1 is written in terms of x0. But mu decoder, to make the optimal prediction of xt-1, we want mu decoder to make a prediction of x0 as accurate as possible. And so this is actually what we need to learn, right? We don't need to learn sigma decoder. The epsilon is just a sample from the standard normal. There's nothing to learn about that. So in order to match our prediction of xt-1 with the ground truth, the only thing we need to do is make a very good prediction of the clean image x0 from a noisy corrupted one. So we don't need to predict sigma decoder. We can rewrite our prediction equation as follows. So we're just making one prediction, mu decoder, which is really just a prediction on the clean image x0. So in the end, a diffusion model is really just one neural network that predicts a clean image x0 from an arbitrary noisified image, or arbitrary noisified version of it, xt. And the loss objective looks like this. Very simple, right? We take xt for arbitrary t's. Our model tries to make a prediction of the clean image x0 to repredict it, and we just try to minimize the prediction loss. So as a quick summary of the diffusion model, it's one neural network that predicts a clean image from a noisy version of that image, right? And so actually the decoder is trying to predict x0, so you can actually convert all those individual black encoder arrows and black decoder arrows into kind of this clamshell figure, where now the encoders all spring from x0 to go to independent xt's, and then for any arbitrary xt, we're also trying to repredict x0. So this is visually what a diffusion model really is. It's like this clamshell across hierarchies. So we've talked about modeling. Our modeling and training objective is trying to predict a clean image X0. And recall that generative modeling is always about modeling and generation, or modeling and sampling. So now let's talk about how we can perform sampling given this model that we've learned. Well, sampling looks like follows. We take any arbitrary position as hierarchy, like xt plus 1, let's say, and because our model is trained to make a prediction on the clean image x0, we can make a prediction, right? And after we make that prediction, we actually add back noise. We go back to encode it, but at a lower hierarchy. And what this does is this actually models one intermediate denoising transition. This black arrow that we want to model to begin with, right, a diffusion model wants to iteratively model these small denoising increments, is really modeled using our model during sampling as making a prediction of a clean image x0 and adding back noise at a smaller level of noise. And then you take that sample, you make another prediction of the clean image, add back noise, and so on and so forth. And that's how you simulate the entire sampling procedure, starting from a Gaussian noise sample. You can just repeatedly apply this procedure of predicting clean image, adding back noise, predicting clean image, adding back noise. And visually it looks like that, but realistically it's because each of those black arrows, remember they're probabilistic decoders, they're predicting a mean and a standard deviation, but really the mean is the same as x0, so that's why visually we go to x0, and the standard deviation is known, and that's modeled by the pink arrow back, which has no parameters. So if we look at the pseudocode, it's quite simple, where the training says, let's take our clean image data from our data set. We can sample clean image, right, x0. We want to learn the decoder to handle arbitrary hierarchies or time steps. So we can sample a t, and we can also sample a Gaussian noise vector because we want to handle arbitrary denoisings. And what we do is we construct xt by using the representation trick, right? Xt is equal to x0 plus alpha t times epsilon. Then our decoder neural network that we seek to train basically makes a prediction of x0 from xt and t. And then we just take a gradient step on that and try to minimize it so that it makes a good prediction of x0. And we repeat this because we want to handle arbitrary data samples x0, arbitrary noise levels t, and arbitrary noise vectors epsilon. So these are the three that we repeatedly sample. We try to learn this. During sampling, it's a procedure that we just visualized. We can start from a Gaussian noise vector, and then iteratively, what we'll do is we'll make a prediction of the clean image. That's this prediction, x hat sub theta of xt and t, and then we'll add back a level of Gaussian noise at a lower level to basically make a sample of xt minus 1. This is the reparameterization trick, right? And we can then take xt minus 1 and repeat that and pass it in until ultimately we end up at x0. So we basically go down the denoising chain, and that's how we perform sampling. So as an example, we basically found a way to reverse this Gaussian corruption process. So during sampling, we can start from Gaussian noise sample and clarify into natural images, maybe from Celeb A, CFR10. Maybe we can also do it for higher resolution images. I mean, the principle is the same. Does anyone have any questions before we start talking about different interpretations beyond what we just covered? Okay, cool. So it turns out that training a diffusion model can be done using 3 different interpretations, right? We just said that we're predicting the original image. It turns out that we can also equivalently train a diffusion model by predicting something called a source noise, as well as predicting a score function. So what are diffusion models as a noise predictor? Well, we recall that the objective we just derived is predicting a clean image x0 from a noisy version xt. And further recall that when we create xt, right, following that pink arrow, we do so using the reparameterization trick, which means that xt is constructed as x0 plus alpha t times some sampled Gaussian noise vector epsilon 0. But if we rearrange this equation of how xt was constructed, it turns out that x0 is equal to xt minus alpha t times epsilon 0. We just moved across the equal sign, and we can substitute it into our training objective. We can substitute in x0 for xt minus alpha t times epsilon 0. But since the model already knows xt is passed in as input, and alpha t is also known because it's just like a known parameter that we can set, then really when we read linearization in the following way, our objective becomes trying to predict an unknown epsilon 0. And so equivalently, we can have a neural network that's trying to predict source noise epsilon 0. It still takes in noisy image, xt, as well as timescale t, but it tries to predict a source noise epsilon 0 that was used to generate xt. And let's try to provide some intuition. Recall in the regularization trick that xt can be rewritten as x0 plus alpha t times epsilon 0, right? We visualize it below using the images, right? Xt is the noisy image, x0 is a clean image, and xt was generated by applying some scaled version of epsilon 0. Well, from xt, our first formulation was trying to predict x0, but because xt was generated as a sum of x0 and some epsilon 0, when you make a prediction of x0, you are implicitly making a prediction on epsilon 0, because alpha t is just a constant, and x0 are two unknowns. And so it is actually equivalent to trying to make a prediction on epsilon 0, because that makes an implicit prediction on x0. I guess to provide a small analogy, it's as if I say, I know that numbers in my universe are created from the sum of two smaller numbers, right? So let's say I give you 10, and my xt is like the number 10. I know it's sum from two numbers. If I predict that one number was 2, it implicitly makes a prediction that the other number was 8, right? Because they have to sum up to my known 10. And similarly, if I make a prediction of the second number being 8, it implicitly makes a prediction of the first number being 2, because again, they sum up to a consistent thing that I have access to. So here, when we go from a prediction of xt to make a prediction of x0, it's implicitly making a prediction of epsilon 0. So we could just reverse it. We could just say, let's just predict epsilon 0 instead. And it turns out they're equivalent. So one might wonder why we might prefer to predict epsilon 0 instead of x0 when they're mathematically equivalent. Yeah, Akash?
Oh, yeah. Just a clarification question. On the previous slide, so in this case, when you're trying to predict the noise, do we still need the t as the input?
We do. So,
Oh, okay.
yes, because let me put it this way. xt was generated from x0 and epsilon and a fixed epsilon 0 with a scale of alpha t.
Yeah. But
And
yeah.
Yeah.
I'm just curious to know that would it be possible to do it without? Yeah, I mean, sounds like not, but okay.
basically, you can think of the decoder transition needing t to tell you how noisy your corrupted image is.
Yeah.
So for any of those intermediate transitions, those decoder transitions, you have to pass in t because it tells the model properties about the actual input. In other words, how noisy the input is. If we pass in a very noisy image without any sort of supervision on how noisy it is, it might be hard because you could pass in very, very noisy ones as well as less noisy ones. So I guess what I'm saying is making a prediction of x0 and epsilon 0 doesn't depend on that will always be done. It doesn't depend on t. But we would always need to pass in t to make a prediction because that tells the model how to make a prediction.
Yeah.
But what it makes a prediction of, x0, epsilon 0, that's interchangeable as we show here.
Yeah, makes sense. Thanks.
Yeah. So it turns out that they're the same. One might wonder why we want to predict x0 over epsilon 0 or vice versa. I think in practice, what you'll see in diffusion models, people prefer predicting epsilon 0 because it's just, I guess they found it's more stable in training, probably because of like training stability, maybe in terms of the values that they inhabit. Epsilon 0 is more preferred, but mathematically they are the same. And the other interpretation is trying to predict something called a score function. And so what are like Stein score functions? Well, they take the following form. It's a gradient with respect to x of log probability of x. And intuitively, if we just look at the form, it describes how to move in data space to improve the log likelihood, right? We already have like a log likelihood, log p of x. Well, how do we adjust x? That's what the gradient says. How do we adjust x such that the log likelihood increases, it improves? And intuitively, if we have this like data distribution as shown on the left, like some mixture of Gaussians, the score function just points towards the modes, because as long as you update yourself by following these arrows that point towards the modes, you're going to be more likely. So you're like most likely at the top of these modes. And we'll actually go deeper into what score functions are later in the talk. But I guess for now, to cover the third interpretation of what we model as a diffusion model, we could just actually appeal to Tweedy's formula. Basically, Tweedy's formula says that for a Gaussian, and in particular, we can apply to this known Gaussian for a Gaussian encoding. There exists a mathematical formula that you created that says x0 is approximately equal to xt plus alpha t squared times the score of xt. And this is due to the fact that the distribution is Gaussian. That the distribution of xt is something that has a mean x0 and alpha t squared high covariance. So we can apply to the formula, basically rewrite x0 in terms of xt plus alpha t squared times the score. And now with this in hand, right, our original prediction is trying to predict clean image x0. Well, now that we know through T's formula that there's this reformulation, we can plug it in. And we can say that our diffusion model is actually trying to predict xt plus alpha t squared times this score value. But since the model already knows xt is provided as an input, as well as alpha t, right, it's also known, it's not learnable, we can just make a prediction on this unknown score term, right? So we can actually also shortcut this by learning a diffusion model that predicts a score estimate given xt. And we will dive deeper into what score modeling looks like. But we at least know for now that diffusion models have another interpretation as a score predictor. And what is this relationship between score and noise? We want to provide some more intuition on score prediction. Well, the relationship between score and noise is, it can be kind of gleaned from equating Tweedy's formula with the renormalization trick, right? Where, this first part is Tweedy's and the last part is like the renormalization trick. And we can cancel out the xt's from both sides and then, divide by this alpha t squared. And we can say that the score is actually equal to a negative scaled version of the source noise. And why does that make sense? Well, the score tells us how we should update noisy image xt to have higher likelihood. In other words, we want to update xt so that it becomes more likely, it becomes a cleaner image, because clean images have high likelihood. And how should we adjust noisy image xt to become cleaner? Well, we should actually move away from the source noise vector that was applied to x0 to make xt. Right? Xt was generated as a corruption of clean image x0 using source noise vector epsilon 0. So to clarify xt towards x0, we should move away from epsilon 0. So we should, that's why it's a negative scaled version of the Gaussian noise that was applied to corrupt the image. So as long as we move away from the Gaussian corruption that was applied, we are clarifying the image, we're improving the log likelihood. So a preliminary summary of diffusion models is that it's really just one neural network that predicts a clean image from a noisy image. Right? The objective is quite simple. Sampling procedure, we simulate those intermediate decoding arrows by using our model that learns to predict a clean image, add back noise, predict clean image, add back noise, etc. I guess this is like another helpful visual of what's going on. And we've also learned 3 different interpretations where a diffusion model can be seen as modeling explicitly x0. You can also learn diffusion models to predict source noise epsilon0 or a score value. So let's talk about predicting the score. And to take a step back on providing intuition on this beyond just applying this mysterious Tweedie's formula, we can build some more intuition on what modeling score is and why it's done. So recap of generative modeling, like we have maybe this unknown data distribution, right? Maybe, for example, it's modeling natural images of dogs. And we want to approximate this with our model distribution, usually model as a deep neural network that hopefully can take in arbitrary images. And when it's of a dog, this deep neural network will predict something of high probability. When it's something maybe like a blueberry muffin, but like it looks like a dog, it should hopefully recognize it and assign low probability to this image occurring. But let's take a look at one approach towards generative modeling, which is probability-based generative modeling. And why is modeling the probability hard for generative modeling? Well, probabilities, and therefore our model outputs when you're trying to, output probabilities, they have to be non-negative. Probabilities also have to be less than or equal to 1. And crucially, they have to integrate to 1 for the entire space. Right. Well, how do we do this for discriminative modeling? Why is this not an issue, modeling a probability in discrimination for classifiers? Well, in discriminative modeling, we have a predefined list of all possible outputs, which are our labels. And so when we predict logits, we can just softmax over them to produce valid probabilities. Right? We pass in a dog image. We have a fixed number of labels, let's say like 10 animal class labels, right? It's predefined. So then we can predict 10 logits, and when we softmax over them, we convert the probabilities. We know for sure that because it's softmax, all the values are non-negative, they're less than or equal to 1, and they sum up to 1 for the entire space. So this was fine for discriminative modeling and classification. But why is modeling probability hard in generative modeling? Well, in generative modeling, we're not modeling a probability over all labels for an image for a fixed set of labels. We're modeling the probability of all possible images occurring at all, right? Some images are should have high probability of occurring, but maybe a very noisy garbage image should have low probability. Right? In GenMo, we're trying to model a probability of all possible images. But there's no way that we can pass everything through our model, compute all the logits, and softmax over the result, and then optimize from that. It's intractable to do inference for all possible images. And or there are ways that we can try to do that, but it would place a lot of architectural burden on our network to force it to output valid probabilities. But neural networks are really good at producing flexible, unconstrained values. They're not very happy when you clamp things or whatever. Neural networks naturally prefer to predict whatever they like: negative, positive, large, small values. And so a simple observation to try to bypass the modeling, direct modeling of upper probabilities is we try to rewrite, probability distributions in the following way. We can rewrite an arbitrary probability distribution as 1 over z sub theta, or normalization constant z theta, times e to the negative f sub theta of x, where now f sub theta of x is a function called the energy function. It's called the energy. And now if we use a neural network to model the energy, it's great because the energy is a flexible, unconstrained value. It can be positive, negative, large, or small, whatever you like. And this reformulation is a concept from thermodynamics, like rewriting probability distribution in the following form. And once again, z sub theta is a normalization constant, which is just integrating over all possible inputs x to make sure that when we integrate, or to make sure that the entire thing sums up to 1. Now, with this reformulation, we've divorced the probability rules from what we need to model. The neural network is now happy because it doesn't need to model anything that respects the probability rules. we can model something unconstrained and then convert it back into a valid probability. And I guess we can also understand why, like how it's being converted back to a probability. For a flexible unconstrained prediction of the energy, the exponent will make sure it's always non-negative, which probabilities are. When you divide by the normalization constant, you know that the resulting value will always be less than or equal to 1, and it will also integrate to 1. And you might be curious why there's a negative sign for the energy. Well, this is a legacy concept from thermodynamics, where the idea is that things that have high energy generally have low probability. So maybe a very chaotic state where things are always like bouncing around and like, super chaotic. When we observe a state, we say that it is the low probability that is in that high chaotic state with high energy. Generally, things like to be stable. And so when you have low energy and things are very stable, generally that corresponds to high probability. So that's why we have that negative sign to invert the energy. So hopefully like this reformulation makes sense. But it's nice now that we can focus our attention on modeling this flexible and constrained energy function. So in energy-based generative modeling, the idea is, well, let's just model the energy function using a flexible neural network. So f sub theta of x is called an energy-based model or a normalized probabilistic model. And maybe what is a naive way to train our energy function? Well, we can make a prediction of the energy and try to reinterpret it as a probability, convert it back to a probability, and we can maximize log likelihood as before. But what is the problem with this very naive formulation? Well, the problem is that it's generally intractable to compute this normalization constant because we have to integrate over all possible x, right? And whereas this can be done for simple parameterizations, maybe like Gaussians, is intractable for like complex parameterizations, which we generally want to use to model the energy network like f sub theta of x. So this is generally intractable to train energy-based models in the following way. So we're once again at an impasse, but we can try to break free by making another simple observation. And this observation is motivated by trying to avoid calculating this expensive intractable normalization constant. Well, we recall that z sub theta is a constant that only depends on parameters theta, right? Because we're integrating over all of x. So if we take the input gradient of the log of the probability, so take the log of both sides of our reparameterization, take the input gradient, the gradient is directed to x. Well, the log will separate out the multiplication terms, will separate the normalization constant from the rest of the equation. And because we're taking the input gradient with respect to x, z sub theta doesn't depend on x as a constant, that only depends on parameters theta, that goes to 0. And the input, and for the second term, the log will get rid of the e. So actually this simplifies to the negative input gradient of the energy function, which we can approximate as a neural network directly, right? We could model the energy function of the neural network, or we could model this negative input gradient of the energy function with its own neural network, which we call the score function, which approximates the thing on the left. Okay, the gradient is right to x of log p sub theta of x. This term that we can try to model directly using a neural network is called the score function. And we return to the slide of trying to understand intuitively what a score function is. Again, it tries to describe how to move in the data space to improve the log likelihood, and is defined for the entire data space for any arbitrary x. It's like it defines a field. So basically, for any arbitrary point, right, the score basically is the arrow that points towards the mode. For these points, etc., you can just showcase the arrows. And because it's just defined for the entire space, we can actually just visualize the score field by taking maybe a grid of points and visualizing the arrows. We see that they all point towards the modes. We can just care about the arrows itself. So in score-based generative modeling, which is I guess built off energy-based modeling, which was itself built off probability-based modeling. The idea here is let's just model the score function using a flexible neural network. And it's nice because the score is still an unconstrained value, which is attractive to model directly. And how we can train it? Well, we can minimize the Fisher divergence between the ground truth and predicted score. Really, you can just look at the equation. It looks pretty intuitive. We have some ground truth score. We want to minimize the difference between our predicted version of that score with the ground truth one, with expectation. Intuitively, this is minimizing the L2 distance between our score model and the ground truth score. This is kind of what it looks like, maybe for a simple case mixture of Gaussians. What we showcase here is like the green arrows are the ground truth scores for the samples that we observed during training. The red is our prediction, and in the middle, that black arrow kind of shows what the model thinks the overall score field will look like over training time. And we can see that after training, on the right, our predicted score field quite closely matches the ground truth one. So we're able to train a good score estimator. And to drive the point home that score-based generative modeling is a way to implicitly model the energy function s of theta of x, right? Call that score is equal to negative input gradient of s of theta of x. So when we're learning the score, we're learning an implicit energy model. We can visualize the learned energy along with the score estimate below. So on the left, areas of low energy, which correspond to high probability, are denoted in dark shades of blue. In the middle, we're showcasing the score field, right, that point towards the modes. And when we overlay them, we can indeed show that the arrows that we learn in the score prediction are pointing towards deep pockets of blue. So we've just talked about modeling. Once again, in generative modeling, the flip side of the coin is sampling. So let's talk about how we can use a score prediction model to perform sampling of natural data samples. So what can we do with the score-based model? It's just a bunch of arrows that point towards modes. Well, we can apply something called Langevin dynamic sampling, proposed by Mr. Paul Langevin, shown on the top right, to basically use predicted scores to draw natural data samples in the following way. We can start from any arbitrary xi, maybe a point in the space, and from there, naturally, to move towards the area of higher likelihood, we just follow the learned score. So the first two terms is for any point in this data space, we should just follow the score that's computed for that xi, and that will bring us to something that's more likely, a cleaner data sample. But we also add this scaled epsilon term. This epsilon is a sample from a standard normal. And you might wonder why we add this term. Why we don't just use the first two terms, aggregate them, and just do that, because we just follow the arrows up to a mode. Well, it turns out that adding some form of stochasticity in the form of a standard Gaussian noise sample is useful, particularly for modeling initialization points along the boundaries. Suppose that you're along the boundaries here between these two modes. Intuitively, when I draw a sample, I want it to have just as good a chance at arriving at the top mode as the bottom mode. But if I deterministically follow my learned score function during inference, right, I will just always follow the one path up to a mode. No matter how many times I start from that same initialization point around the boundary, I'll always follow it up to one mode, no matter what. But if I add some sort of Gaussian noise stochasticity and it jitters, then there's a chance that it'll actually break free and follow the other mode. So having stochasticity in the sampling path is quite nice, because it gives us a chance to generate samples from multiple different modes for the same point. And if we iteratively apply this, right, from any initialization point, we'll eventually converge, as we see in the visualization on the right. We eventually converge around the modes of true data samples. So this is how we can use a score estimate to perform sampling. I like the idea of throwing darts. I visualize Langevin dynamic sampling as throwing a dart on the data space and then just following the computed score with this stochasticity and just traversing the data space until you ultimately get up to the peaks or the modes. But yeah, I just think of, I just like to think of Langevin sampling as just throwing darts and following the path that you learn. And once again, to drive the point home, oh yeah, Aman.
Just a quick question. So if I understand it correctly, we can also use epsilon for like reproducibility as well. If we have like some fixed value, so we can use it to reproduce same samples again. Is it correct?
Sorry, what did you mean by reproducibility?
Like if I want, so for a given input, I want to like have the same output in generative modeling. So can like an epsilon help in this way?
I'm not sure about reproducibility because at each time step, you're resampling another epsilon noise value. Like the path, as it goes up to the modes, it just, it like jitters.
Oh, oh,
Yeah. I guess you can also see that example here. So I haven't really been monitoring the comments because I'm looking at the slides. But if you have like pressing questions, just directly like raise your hand. That'll get my attention. But yeah, all these GIFs are made through Matplotlib. Okay, so yeah, I guess it drives the point home, like the score prediction and sampling, right? How we follow the score is equivalent to like, going to areas of low energy, right? We can see that the same path ends up in deep pockets of blue. And it's the same as like reversing this probability, this likelihood graph for a data distribution, like going to areas of like high likelihood, right? And similarly, it is the epsilon that we apply during longitudinal dynamic sampling at each time step that allows us to start from a point like the one shown here and have a just as good a chance at arriving at any of these three modes. Okay. So it gives us some diversity of sample. So score-based generative modeling, pioneered by Yang Song, the idea is we'll have data samples, we'll perform score matching, and then we'll use Langevin dynamic sampling to generate novel samples around those data modes. But what is the problem with vanilla score matching? Well, if we expand out the equation, and it looks as follows, and also just think about it intuitively, there are some issues, which is that our model of the score will not actually be able to learn the low density regions well. Why not? Well, during our data collection, like we generally train on good data that's centered around the modes. We don't actually see very many examples of, low, like samples from like low density regions. So we don't really have good training signals for them. And even when we do have good training signals on them, because of our objective, our terms are scaled by P of X. And so it always has a high preference for things that have high likelihood anyways. And so naively with vanilla score matching, training with this objective, we will not actually learn low density regions well. But the problem is that might be fine for modeling, but when we perform sampling, the flip side of the coin, using Langevin dynamics, we most likely initialize as noise. When we throw a dart to just start, from a random place in this data space, and then move to try to generate a good data sample, generally that dart will not fall in areas that are already like good data samples. If we had a great sampling technique that could do that, maybe we wouldn't need to go through all this issue. Generally, our initialization will be in areas of low density. So it's actually quite bad that our modeling part does not really support what we need for sampling, right? We need accurate estimates in low density regions for sampling, but the modeling by default doesn't really provide them. And so what is the solution for vanilla score matching? We can try adding Gaussian noise to the data density. And that is like a proxy to that is taking true data samples and just corrupting with Gaussian noise, like the corresponding data distribution would basically be a perturbed, expanded version of the for each mode. in the data space. So each of the modes now like expand and they cover more of the data space, modeling like a Gaussian corrupted version of the natural data. And if you add a lot of Gaussian noise, well, now the perturbed scores, the scores for this perturbed density cover more of the space. You see more of them, and you can learn accurate score predictions for this perturbed density, right? And now the question becomes, how do we choose an appropriate noise scale for the perturbation process, right? If you add large amounts of Gaussian noise, it can cover more regions for better score estimation because you see more of the data space. You have better estimates, and so when you initialize there, you can follow more accurate scores. But adding large amounts of Gaussian noise will overcorrupt the data and alter it significantly from the original distribution. So even if you follow up the score, maybe the result is like a very corrupted version of the natural data that we don't want. Conversely, if we add small amounts of Gaussian noise, it'll corrupt the original data distribution less, and so your final samples will be more accurate. But we once again run into the problem that it doesn't cover the low density regions as well as we would like. So we still have like pockets of, or like desert regions of inaccurate score estimates. And so the approach that Ying Song and his co-authors proposed was, why don't we have both? Why don't we simultaneously model multiple scales of noise perturbations of the data distribution simultaneously? And so this is kind of what it looks like. We still have our data distribution, but we corrupt it with different levels of Gaussian noise. And we can also visualize the score fields associated with these perturbations of the data distribution below. And we can model it by trying to model the score of each of these noise perturbed distributions for, let's say, T levels of noise perturbation scales. And we can model this as a neural network, which we call the noise conditional score network, which is once again one consistent network that conditions on the noise level and predicts the score for it. The training objective is a weighted sum of Fisher divergences for all noise scales. We generalize the original vanilla score matching objective, the Fisher divergence there, to now having T of them, right? We sum over T, and maybe we can scale it with whatever weighting that we like. But really, we want to learn all of these T noise conditioned score predictions simultaneously. And once we have these T noise conditioned score networks, we can once again perform sampling, this time not through vanilla Langevin dynamics, but through annealed Langevin dynamics sampling, which is basically saying, let's run Langevin dynamics sampling for each noise level in sequence, iterative, where we initialize the next noise level Langevin dynamics sampling with the results of the previous one. So here we visualize that for a high corruption, right? We have accurate score estimates for a corrupted version of the data, but it doesn't matter. We can follow it for some time steps. Then we can, it has moved at least nominally towards some of these modes, maybe not that much. But once we stop that, we can initialize it for the score predictions for sigma 2, which basically has modeled how to move it towards less corrupted versions of the natural data. We continue following up with this prediction, and it gets closer and closer. And finally, because those initializations will be close to the ones at another lower level, we keep following up these predicted scores for steadily decreasing amounts of Gaussian noise perturbations, and ultimately we can arrive at essentially the modes. And so what we just described is a way to go from something that's very heavily noised. You can imagine that at the extreme, we've added so much Gaussian noise that it is indistinguishable from like a Gaussian noise vector. And what we describe is following the score over many hierarchies into some clean data mode. And so some examples of this shown here are like going from standard noise into like images from CelebA and C410. And I showed you this slide earlier for diffusion models, but actually I tricked you because they were actually generated by this score-based modeling approach from Yang Song's paper. But actually, I didn't really trick you because the punchline is that these two formulations can be shown to be equivalent. And so we'll try to unify these interpretations of score-based generative modeling over many noise levels with annual Langevin dynamic sampling. We'll try to unify it with the first part of the talk, variational diffusion models, where we're trying to denoise over many hierarchies. So as a review, variational diffusion model, we want to learn a denoising decoder, right? It takes an xt and time step t and predicts clean image x0, from which we can generate the next step slightly denoised sample xt minus 1. Recall that this is done using the root parameterization trick, right? Our predicted xt minus 1 is generated from our prediction of x0 and alpha t minus 1, which is known times epsilon. So the ground truth denoising sample of xt minus 1 is x0 plus alpha t minus 1 times epsilon. That's the root parameterization trick. And here, when we perform training, our training objective is trying to predict x0, right? So under this formulation, our loss objective is clean image x0. How good is our reprediction from xt? Right? And this is equivalent when we substitute in using the representation trick. This is equivalent to trying to make a prediction on epsilon 0, right? Because we know using a representation trick, x0 is equal to xt minus alpha t times epsilon 0. We can plug it in and say the only unknown term here in this formulation for the ground truth xt minus 1 is epsilon 0. So equivalent formulation is linear decoder neural network that predicts epsilon 0. And just another equivalent formulation is plugging in Tweedy's formula, saying, for x0, Tweedy says x0 is approximately xt plus alpha t squared times the score of xt. When we plug it in, we can say that our ground truth, xt plus minus 1, is equal to, this long equation where the only unknown is the score prediction. So equivalently, we can say our diffusion model can be thought of as a score predictor with this loss objective. So what I'm going to try to do right now in unifying these generative models and making the argument that they can be shown to be equivalent is, well, once again, a generative modeling in my mind is composed of two things: modeling and generation, modeling and sampling. So if we can show that the modeling objective, the training objective, is the same, as well as the sampling procedures being the same, then we can show that they're really equivalent. So let's take a look at the loss objectives, the modeling portion first of generative modeling. Variational diffusion models, we have this loss objective, right, that we derived in the first part of the talk. Well, we can compare it with score-based generative modeling and that objective, right? Hierarchical VAE interpretation shows that we can basically use a network to model the score function, arbitrary noise corruptions, right? It takes the following form, where we aggregate it over multiple time steps t. And in score-based generative modeling, we're also using a one network to model the score function at arbitrary levels of Gaussian noise corruption, learned in the following way. And we can see that the objective really is the same. We're learning it for multiple timescales, trying to minimize the difference between some ground truth and prediction of the score. And for this expectation and this weighting, we can find parameterizations for the weighting to make them equivalent. So functionally, the training objectives for hierarchical VAE, formulation of diffusion model, and the score-based generative modeling, they are equivalent. Now let's talk about sampling. So we know that when we sample, we're trying to go from xt to xt minus 1. And we do so by following our predicted score. So we have this equation for variational diffusion models of what xt minus 1 should be like when we're properly sampling. Let's compare it to Langevin dynamics. Let's ignore annual Langevin dynamics sampling for now. Oh, sorry. We should be comparing this to annual Langevin dynamics sampling. Maybe a bit confusing, but let's take a look at the formulations of sampling for both approaches. Annual Langevin dynamics sampling says we start from x1, we improve it by following a learned score and add some stochasticity so that we have some training or some sampling diversity, right? And that's how we update to the next level, xi plus 1. And in the denoising transition for hierarchical VAE, right, we have this noisy version xt, we apply some scaled version of the score, as well as some epsilon to generate the cleaner image xt-1. So the xi and xt, they're equivalent. They represent the more noisy version, right? Samples from a noisier version of the data that we want to use to go to a slightly less noisy one. The score prediction is what we follow, is the same, and they're scaled by their own constants, but their constants, they don't matter. And we also always apply an epsilon term, but they have slightly different interpretations. Langevin dynamic sampling says that this epsilon term is for like sampling diversity, right? It's nice that we can jitter and go to different modes. Whereas here in the hierarchical VAE formulation, the epsilon's interpretation is the reprioritization trick, because this first part is essentially x0 and xt-1 is generated as a sample from a probabilistic decoder using the reprioritization trick, right? But it's very interesting that they have different interpretations. You can think of them in different ways, but the sampling procedure is the same. So annual Langevin dynamic sampling can be shown to be analogous to Markov chain procedures, like ignoring the constants. What we're doing is the same. So to visualize it, like on the top, we're denoising over multiple hierarchies iteratively, like following the black transition decoders. On the bottom, we're also clarifying something from something very noisy to something clean. Really, they're both trying to do the same thing in the middle, which is go from something very noisy to a clean sample. And so we've unified the two interpretations. We've shown that there are two equivalently valid ways to describe a diffusion model, where one takes the perspective of this Markovian hierarchical VAE, samples are steadily denoised through hierarchies, and another takes the perspective of energy-based models and score matching, where we iteratively refine an input through noise levels, because we need that to get good estimates of the score function. It turns out that these interpretations are two sides of the same coin. Does anyone have any questions before we move on to conditional diffusion? Okay, so far we've been learning an unconditional diffusion model, piece of theta of x, right? But really, what we get very excited about is trying to learn conditional diffusion models. We want to learn models where we can generate fancy images conditioned on text. And so the big question now is, how do we incorporate conditional information such that we can control the data that we generate during sampling? And so suppose we have conditioning information that we present with y, and now we want to learn p sub theta of x given y. Well, an unconditional diffusion model, which we just spent like the first, I guess, hour and a half talking about, is really just this one neural network takes an xt and t and predicts clean image x0, right? Well, it turns out that if you want to train a diffusion model that conditions on some conditioning information y, you can very simply just pass it in as another input to this model, right? Just throw it in there as another input. It can condition on it when predicting x0, right? Similarly, for all three different interpretations, you can do so for epsilon prediction. You throw in y as an input. It'll factor that in when predicting epsilon 0, the source noise prediction. It's similar for score prediction. For the score prediction network, noise condition score network, or what have you, you can also throw in y. So are we done? Well, not quite. The caveat is that a conditional diffusion model trained by the simple conditioning, where you just pass it in as just another input, it can ignore or downplay the given conditioning information. There's no guarantee, actually, that when it makes this prediction of the clean image, that it factors in the y. Maybe during training, it just learns to zero out all the things that that look at y. Like, it could just not factor it at all or downplay it. Or what if we care a lot about heavily respecting our conditioning information? Why? Well, there's no natural mechanism to do it when we just throw it in as just another input. So this kind of intuits the idea of guidance, And the idea of guidance, or the motivation behind guidance, is trying to provide more explicit control on the amount of weight that the model gives to the conditioning information, potentially at the cost of sample diversity. It really seeks to answer how much should our generated X match provided conditioning information Y. It wants to give us a lever which we can manipulate such that maybe when we increase some term, our output generated X heavily respects Y, or maybe if we don't care about Y too much, we can also decrease it, but it wants to give us control. So let's take the score-based perspective of diffusion models to try to explore the concept of guidance. Now, we are interested in learning the conditional score, P of xt given Y, rather than unconditional score, which is just gradient of log P of xt. And we can very simply reformulate this conditional score using Bayes' rule, where we can take P of xt given Y, we write it using Bayes' rule, and apply the log to separate out the multiplication and the division. And because the gradient, you recall, is computed with respect to xt, this last term, the gradient of log P of Y, goes to 0. And so it turns out that the conditional score will simply reduce to an unconditional score plus some adversarial gradient, the gradient of the log of P of Y given xt. So the unconditional score is something that we're very familiar with because that's what we've been modeling the entire time earlier on in this talk. But what is this adversarial gradient term that we now have? Well, P of Y given xt can be thought of as a classifier, right? Think about just classification, taking an input xt and maybe Y as some label. If we're thinking about, let's say, our conditioning information Y is like a class label, we're doing like class condition generation, then P of Y given xt is really predicting the label, the correct label from your input xt, even though it's a noisy version. And what does taking the adversarial gradient of this classifier mean? Well, the adversarial gradient is computed with respect to xt. So for a given image, let's say we have this blueberry muffin image, the logits are, for a very simple classifier, dog is 0.5, cat is 0.5, is very confused. What the adversarial gradient says is how do we adjust this muffin image such that the correct label, dog, is predicted with higher likelihood. And basically, it's like pixel-wise adjustments to this muffin image to be more dog-like, such that the label for dog is predicted with higher likelihood. And what this is basically saying is that modeling the conditional score, how we should adjust xt during sampling, can be done by querying the unconditional score function, so moving along the unconditional score to bring your xt towards any natural image, as well as updating this image such that now a classifier will be more likely to predict the conditioning information that you provided. So this classifier is attempting to tell us how good the noisy image matches the conditioning label or conditioning information, but we cannot directly apply maybe pre-trained out-of-the-box classification models because the input for this classifier is xt. So this must be trained, it's like Gaussian noise versions of clean images, so we must train this for arbitrary noise levels. But once trained, we can query it for updates on how to make it respect conditioning information more. And we can combine it with the unconditional score, maybe with the scaled version for this classifier guidance term, to ultimately compute a coherent conditional score. So this shows us the power of guidance because now, when you deconstruct in the following way, we can scale gamma flexibly. If we have a very high gamma, we're going to make xt update in a way that heavily prefers respecting conditioning information Y. If we don't care about that so much, we can directly set gamma to a very low value. In the case that we don't care about conditioning information at all, we can set gamma to 0. But guidance gives us this flexibility to control how much we care about conditioning information. So let's try to visualize this. During sampling, suppose we have a very simple example where we have like animal images, different modes represent different animals, like cats and dogs, monkeys. And And the unconditional score looks on the left, right? We have all the arrows point towards the modes. But let's say that we want to generate a monkey image. Well, the conditional score will only point towards that monkey shown on the right. And we could show that we can sample something that is monkey-like in the following way. We're going to follow conditional score, which is computed, which is initialized at any arbitrary point, right? We just throw a dart on this data space as our initialization point. But now we're going to follow conditional score, which is computed in the following way. We follow the unconditional score, which brings us towards any natural image. And we also follow, adjust our image following this adversarial gradient with respect to some classifier with some scaling term, and that will combine to show like the conditional score that we ultimately follow during sampling. And because of this gamma, we can scale it so that it can be large or small, depending on what you like. And you can see that overall, it'll mostly like veer towards maybe the monkey mode. Well, a question you might have is, why don't we just use this adversarial classifier, or this adversarial gradient of the classifier, right? Why don't we just keep following it up to a monkey mode? Well, you might have seen before that this is kind of like optimizing the input. Yes, Mayan.
What's the monkey mode here?
Oh, sorry, this is just a very simplified example. Like when we sample, we want to go up to a mode. What I'm trying to say is like when we care about a particular mode, like I don't want to generate any animal image. I want to generate like particularly a monkey image. What we actually want is to eventually move towards around the monkey mode, right? But how we do that is, you know, this is the score that we followed. The purple is what we ultimately follow as a conditional score to go towards the monkey mode, right? Because we care about the label Y, which is a monkey. But how we do that is we follow an unconditional score as well as a adversarial gradient computed from classifier. You can see that overall, it'll roughly curve into that monkey mode area. But like maybe a question is, why don't we just follow this adversarial classifier, like gradient, or adversarial gradient of the classifier, and just arrive at the mode? Well, it turns out that this is kind of like optimizing the input. Recall that like the classifier itself is a neural network. And when we optimize our input such that the neural network classifier is very happy, you can do that such that, you know, for some inputs you've heavily optimized, it'll output the correct class with 100% probability. But when you visualize the input that you've optimized, you know, let's say for MNIST digits, it looks very unnatural. It looks almost nothing like the digits that we recognize. But somehow they've been optimized to make the weights of the classifier very happy to output the correct label. So if you just follow the adversarial gradient of the classifier, you're optimizing the input, you will not get natural looking images. And so that's why it's, you know, ultimately we want to balance, because this term, the unconditional term, essentially tells us how to move towards natural looking images, right? It doesn't matter what image it is, it'll look natural. And this term will say, at least make it respect a class. You have to combine both to ultimately get things that respect a class while still looking natural. Right. Oh. Yeah, Akash.
So if I understood correctly, the images that you showed for the unnatural images for the MNIST dataset, those are still valid images for the classifier to predict them to be digits, but they're just unnatural.
Yes. Yes. Like that's if you just purely optimize the input. If you only update following this, it's like I forgot the exact term in the field. It's like input optimization. You get something, and some people have tried doing this for, I guess, interpretability of neural networks. It's like for a label like a dog, what are like, you know, the filters or features that activated the most. Maybe you can glean that from optimizing an input very heavily, so that, you know, the classifier will say this is a dog with 100% confidence. But when you look at it, you can maybe see that it doesn't look natural, but maybe get some insight into what kind of dog-like features the classifier really respects. But that's not what we like. we want to generate natural looking images that also respect some class. So we cannot only follow this adversarial gradient of the classifier.
Interesting. Thanks.
Yeah. Okay, so the problem with classifier guidance is that we have to have two models, right? We have to have, of course, the unconditional score prediction model or unconditional diffusion model, but we also need to separately learn this this classifier model, and we have to learn it because it takes in as input like noisy images. We don't have access to a lot of that from like pre-trained classifiers. And so a big question is, can we perform guidance without requiring to learn two models? And Jonathan Ho was able to formulate classifier-free guidance, and we'll walk through how it's derived now. It's quite simple. If we revisit the score of a conditional diffusion model, right, after Bayes' rule and applying the gradient and the log, it looks as follows. If we rearrange things across the equal sign, so we move, you know, the unconditional score across the equal sign, if we move across the equal sign, then what we get is that this classifier, this adversarial gradient of a classifier can be rewritten as a conditional score minus an unconditional score. Okay, so now if we take the classifier guidance formulation that we just derived, right, we have our conditional score that we want to follow during sampling. Where we rewrite it as following an unconditional score plus this classifier score. We can plug in this rearrangement that we just did to get the following equation. So it says maybe the conditional score that we follow during sampling should be this unconditional score as well as this plugged-in version, which is written only in terms of a conditional score and unconditional score. And when we distribute the gamma and rearrange, right? We can distribute the gamma and aggregate them. We can say that maybe the score that we follow during conditional sampling can be written as a conditional score as well as an unconditional score. Now, this might seem very strange. This is what classifier guidance looks like. And this might seem very strange to you. You might be scratching your head. You're like, well, what happens if our gamma is 1? Well, if our gamma is 1, then the unconditional score term just disappears, and we just say that the conditional score is the unconditional score. So we should just follow, a conditional score is a conditional score. We should just follow a conditional score prediction, which is equivalent to our initial thing of just passing y in as just another input without any guidance skill. But interesting thing happens if we try to set gamma larger than 1. If we try to set gamma larger than 1, well, then what we're saying is how we should move during conditional sampling is we should move according to some computed conditional score and move away from some computed unconditional score, because this will turn negative when gamma is larger than 1. And what at an intuitive level, what that's saying is like we should move towards something that heavily factors in the conditioning and move away from a prediction that doesn't factor in the conditioning at all. And that's the way that classifier-free guidance tries to respect y, conditional label y. And once again, this guidance, it provides us a nice lever which we can control the behavior. So we can flexibly scale gamma as we please to control whether we prefer factoring in the conditioning information a lot or not very little or not at all. So in our classifier-free guidance, the question is, how many diffusion models do we need to train? Right now we're trying to predict 2 different scores, a conditional score and an unconditional score. Well, we can model the conditional score using its own decoder neural network, right? That takes in input y along with xt and t. And we can also have an unconditional diffusion model separate from that, that just does what we did before, takes an xt and t and predicts the unconditional score. So ostensibly, we still need to learn 2 models. So maybe it isn't much better than classifier guidance, where we also need to learn 2 models. But it turns out that If we do formulate with classifier-free guidance, we can aggregate it into one score prediction model, and we can basically use this one unified score prediction model to predict an unconditional score as well as a conditional score, depending on whether or not we zero out the conditioning information. So we can combine it into one consistent diffusion model where if we pass in y and as it is, then we treat the output score as conditional score prediction p of xt given y. And if we zero it out, maybe with some masking, then we can treat the output as unconditional score prediction gradient of log of p of xt. And we can train one consistent neural network model to produce unconditional scores and conditional scores by just performing dropout during training of the conditioning information. So like with some percentage probability, we will like mask out y during training and treat the output as unconditional score. And that's how we can combine everything into one model, which is really nice. So classifier-free guidance, I think, is almost like the de facto version used in like the diffusion model implementations, because you only just need one network. You can see some pretty pictures of classifier-free guidance and the images they can produce, right? From Imagen, their website, right? They can condition on text and generate fancy images. And I guess for the final part, we can try to explore some state-of-the-art diffusion models in practice, and sort of connect what we've just learned with what's being maybe actually used. So maybe we cover DALI 2, Imagen, and Stable Diffusion. So in DALI 2, I think their observation is predicated on trying to perform some sort of unclipping. So during clip, which I hope many of you are familiar with, we have an encoder for text and an encoder for image. We try to align the encoded representations, right? Well, in DALI 2, or also known as unclip, what they're saying is we can reuse this learned clip space by saying, let's still encode the text into a clip text embedding. But now, if we learn a model to take this clip text embedding and bring it to a clip to a corresponding aligned clip image embedding, and we learn another model to take that clip image embedding and decode it into an RGB image, well, then essentially what we've learned is a way to go from text to image, right? It's like one text to image pipeline. Well, where is the diffusion model in this pipeline? It turns out that there's a diffusion model that they train to take a clip text embedding and bring it to a corresponding clip image embedding. And what they do there is they will initialize, because the clip image embeddings, the clip embeddings, I guess, across all modalities have the same dimensionality. What they'll do is they'll initialize a standard Gaussian noise vector of the same dimensionality, provide the text clip embedding as conditioning information, and then denoise that into a clip image embedding that aligns with the clip text. Then they'll actually learn another decoder that reverses the image encoding. It'll like deconvolute it back into RGB space. This is also modeled as its separate diffusion model. So actually DALI 2 has two diffusion models. And why they call it unclip, I think, is because you're taking a clip latent and unclipping it back into RGB space. You're reversing the encoding. Imagen is yeah. Ahmad?
So why are they converting the text embedding to image embedding? Because in clip, if we take the semantic similarity of a text embedding and the image embedding, they are essentially very close. So
Yes.
why do they want to like convert from text to image?
Yeah, because there's a notion of alignment. During clip, they've trained these latents to be heavily aligned, right? And what we want during generation is an image that is aligned with your input text. So what they're trying to do is they're trying to leverage the learned alignment from this large-scale pre-training of this clip model, and saying, if I were to take now a clip text embedding, I would want to generate an aligned clip image embedding. Because I would represent an image that would be described by my text. It would respect the text. So that's why they learned that prior model. Right? Then once they have that clip image embedding, then the question is, well, how do we get a RGB image back out of it? And they do that through the learned decoder, which they model as another diffusion model. But yeah, it's because of the learned aligned space from clip that they want to reuse. So in Imagen, I would say it's more straightforward, where they just learn a bunch of stacked diffusion models, like what we described at the beginning of the talk, where you take some text or some large scale, like pre-trained language model that we keep frozen to encode the text into some embedding. And then what we do is we learn a diffusion model that conditions on this text to generate a 64 by 64 image, right? Then a super resolution model that conditions that brings that 64 by 64 image to something 256 by 256, while also conditioning on text, and so on and so forth. So when you stack it, ultimately you just have a pipeline that will condition on text to produce a high resolution image. And what about stable diffusion? Well, if you remember in a very early part of the talk, we said that in a VAE, we learn two networks, right? Encoder, decoder. How many do we need to learn for hierarchical VAE? When we assume that all latent dimensions are the same, we just need to learn 4. Well, it turns out that visualization is exactly what stable or latent diffusion model is doing, where now the latents are described, or the latents are modeled using a diffusion model. So all the diffusion modeling is happening in the Z1 space with the same dimensionality, but X is maybe a larger dimensionality, like a natural image. And so here, and once again, we can throw out the encoders because it's just Gaussian transitions. Here, we just need to learn 3 neural networks. Or I think in practice, they don't actually learn it. They reuse like a pre-trained encoder and decoder for VQ VAE. But now we have 3 components. We have an encoder that brings the natural image X to this latent space. We now learn a diffusion model with many hierarchies over this latent space. And then from that final like good latent Z1, we project it back into X. So that's how stable diffusion works. Oh yeah, I guess I wrote it down. Yeah, it projects small latent space, learns it only for the latent, reprojects it back. And the benefit is, you can, perform this expensive diffusion modeling and sampling procedure over a smaller, cheaper latent space. So it's more tractable. Yeah, you can play with the demo. I guess if finally, just to summarize, we show that diffusion model is simply a special case of a hierarchical VAE, right, with this nice clamshell figure with our assumptions. Special case being like making a bunch of assumptions for a standard hierarchical VAE. We also showed the optimization training objective can boil down to learning a network to either predict the original image, the source noise, or the score function at arbitrary Gaussian noise corruption levels. And we also draw an explicit connection to score-based generative modeling and show that they are equivalent in what they model, right, their objective, as well as their sampling procedure. Right? And lastly, we showcase how to build a conditional diffusion model, like how to build a good conditional score estimate and apply guidance. And I think that's all I had. And I'll stick around for any questions you guys may have. Yeah, that's about it. Yeah, hey, Karthik.
Hi. So for the classifier-free guidance, when it is more greater than 1 and less than 5, the diffusion models does not respond in practicality. But if the strength is greater than 5 and between 8, they respond quite well with the prompt. So why is this happening? Is this something that we need to correct during the training of the diffusion model, or how do we correct this thing?
I think during training, it just matters about dropout. I don't remember off the top of my head what the dropout percentage is. Maybe like every 10% or 20%. That is like standard. But like the first key is trying to get good conditional score estimates, as well as good unconditional score estimates. And as long as you have good estimates, you can keep it frozen. Like the diffusion model during inference, it's not updated, right? And then you can flexibly try different guidance scales at your whim during sampling. You have a lot of control during sampling on what it ultimately produces.
Yeah.
I think that there is probably some magic on finding good values, like,
Yeah.
like 5, 10, or 20 or something, but that's separate from training, right? As long as we have good training of the score predictions, we're fine.
Also, I have another question. So the inference steps, right? It takes the more inference steps we have, the more good quality output that we generate. But the distillation process also gives us better to process less inference steps and get a greater quality of the image. So what is the important factor of this distillation on diffusion models?
Yeah. I'd say that, like, I'm definitely not like an expert on the consistency model or the distillation part, but you can imagine that, after you've learned a diffusion model that can predict a lot of incremental scores, you can try to, take this pre-trained model that does things very slowly and try to distill it into something that hops steps, but hopefully consistently. But you can imagine that because you're hopping steps, it's going to learn to inject more like stronger priors about what's in the image. When you think about steady denoising, there's a lot of chances, because you see a lot of like application of Gaussian noise, there's a lot of chances to flexibly adjust or fill in small grain details at a steady pace. When you're making big jumps, generally you learn to fill in with aggressively, like with details. So it still might have very high quality, but it could be very strong in its learned priors, I would say.
Yeah. Thank you.
Yeah.
Thank you so much.
Michael?
Hey, so I thought the parallel to sort of like simulated, or I guess not simulated, but like annealed like optimization procedures was kind of interesting, and I was wondering if there were any ways to use diffusion for optimization that isn't imitation of existing images, but for things like just general purpose optimization. I guess like in AlphaFold 3, like you're able to train the diffusion model to optimize the protein structure and things like that. So
Yeah. I would say it's not like annual Langevin dynamic sampling, or I guess basically just score-based generative modeling as a whole is not really tied to images. It's just based off the, like, I guess we use images a lot because it's nice and visual, and it got its greatest initial success from that. But really, you can imagine that for any complex data distribution, you can expand its coverage of the whole data space just by adding Gaussian noise. So that approach is it's general, I would say. I don't know if that answers your question, but it's not like just tied to images. You can also use it to model other things like audio and whatever.
yeah, because I saw some interesting works where I guess I'll have a really quick follow-up question, I guess, but like
Sure.
or comment, I guess, but like I saw interesting works where you could generate images that look different from different rotations, I guess, like generating optical illusions in a sort of sense.
Yeah.
And I guess there isn't really a good data set of those types of images. So I guess like it could also be used for exploration or like computational approaches as well. That's what I was sort of asking about. But,
I see. Yeah. Sorry. Well, what was the question or the follow-up question?
I guess the question was just like, do you think there are opportunities for that?
Yeah. I mean, I'm consistently amazed by what people have done. I've also seen like the optical illusion thing. I'm still not exactly sure what you mean by like optimization.
I guess like like the parallel between reinforcement learning and imitation learning, right? Like you could optimize some arbitrary objective, I guess.
Yeah, yeah. There have been some works on that. Let's say like kind of like RLHF for diffusion, to maybe align it with like some sort of preference. And there's been some work on like trying to formulate rewards so that as it goes down the denoising chains, like, you know, certain denoisings will have higher rewards than others, and maybe hopefully steer it towards something that factors in some sort of human preference. I think there's a lot of things to explore in that space. Yeah.
Okay, thank you. Good talk, by the way. Thanks.
Thanks. Mayank?
Yeah, I had a query regarding a slide that you had where you derived the score function. So if you can go back there.
Sure.
So
Let's see. It might be around, yeah, it might be here. Is it this?
yes. So I was a bit confused between the equation one and the second one. So how did not this one? I'm not too sure. This one I understand. If you go back a slide, not
This one? No.
no.
Yeah, I think that was the derivation.
Yeah,
Well,
where you had the score function simply written.
this?
No.
Are you talking about the one where there was the alpha square
Yes,
and
yes.
plus? Okay.
Yeah.
Oh, the Tweeties thing.
Yes.
Like this.
Yeah, there was, I think it's probably in the next slide where it shows like, you know, xt plus alpha t square and then gradient of log pxt, and then also shows xt minus alpha t epsilon, like that, right?
Oh,
That's the one, I believe.
I see. It's something like this.
Yeah. This
Okay.
one.
Yeah.
So could you please expand on this a bit? The second and the third equation that you had.
Okay. So the main idea is like our ground truth denoising sample xt minus 1 is written in this following equation. I hope maybe everyone's happy with this, right? Because when we make a prediction, because this is, we still treat this as like a probabilistic decoder, xt minus 1 samples are generated from a probabilistic decoder as using the root generalization trick as the mean plus the standard deviation times standard noise sample, right? So our ground truth and also our prediction xt minus 1 will roughly take this form, where if it is a ground truth xt minus 1, x0 is the true clean image. If it's a predicted xt minus 1, then this x0 is actually our predicted x0, right? So xt minus 1, because of the three different interpretations of our training objective, x0 is equal to xt minus alpha t times epsilon 0. And this goes back to, sorry, I might jump back and forth. This goes back to our, where do I have it? I went too far back. This, right? Where the idea is like making a prediction of the noise is the same as making a prediction of the clean image for a given xt that was composed of a clean image and a noise, right? Like this xt was generated from a given x0 and a sampled epsilon 0. And once you generate this xt, that xt is fixed. Now, from that xt, our diffusion model in the image prediction formulation is trying to repredict the given x0. But because xt, which you're given, was created from x0 plus epsilon 0, and this is just like a a constant. When you make a prediction of x0, it implicitly makes a prediction of what epsilon 0 was. We call this special epsilon 0 the source noise, because it's, I don't know how better to say it, except it's fixed with respect to xt. Right? Before generating xt, the source noise is a sampleable thing, but once you sample it, you fix that, you add x0 to it, you generate xt. Now from xt, you're trying to predict x0, and that's the same as making a prediction of epsilon 0. So there's an equivalent formulation that says, well, why don't we try to predict epsilon 0, and that makes an implicit prediction on x0. Anyways, you have this equation xt, which is equal to x0 plus alpha t times a special epsilon 0. And all that we're saying here, or I guess here, is that you can substitute in for your prediction of x0 with this xt minus alpha t times epsilon 0, right? Because they're equivalent. And when you substitute that in, your equation expands and looks messier. But really, when you look at each term, you're predicting xt minus 1 from xt, but you know xt, you know alpha t minus 1, and epsilon in this case is a new random sample that's used to generate xt minus 1. But what you do not know was the source noise epsilon 0 that defined xt. So here, our objective is predicting an epsilon 0. If we have an epsilon 0, then we can go from xt to xt minus 1 by subtracting alpha t times that prediction plus alpha t minus 1 times our random noise sample. And that's our predicted xt minus 1. So is that clear?
Yeah, thanks.
Okay. We do the similar thing for Tweedy's formula, where in the first part, we just say, there is a formula because we can exploit that the pink transitions are Gaussians that basically says that x0 is approximately equal to xt plus alpha t squared times a score. And we can once again plug it in for x0 to get this expanded equation. But once again, the only thing that's unknown that we need to predict is this score. And so once we have this score prediction, we can go from xt to xt minus 1 by saying, well, xt, we add the score and also add some stochastic noise, another Gaussian sample. And this is what we draw parallels to with the score-based generative modeling formulation. We're also starting with something noisy, following a score, and adding some stochastic noise. Yeah, I hope that clarifies.
Okay, so this is only in the case of stochastic noise.
It is only exploitable because our transitions are Gaussians.
Oh, okay. Okay.
Where did I place that? No, it's too far. Yes. So because our Gaussian transition, like the distribution of each xt given x0, those pink transitions take the following form. Tweedy's formula can be applied for Gaussians, or I guess generally Tweedy's formula applies to exponential family distributions, but it can be applied for this this particular transition to produce the following equation, which we can plug in and exploit and say that we actually want to model the score. There's I kind of hid the derivations because I want to focus on the intuition. But if you're very curious about the math behind it all, you can dig into the tutorial or send me an email about that after. But there is an equation that we can leverage, and then we also build up that same formulation through annual Langevin dynamics, through score-based generative modeling, and then we tie it together, show that they're equivalent. Yeah, so hopefully that provides some additional context.
Thanks.
Will you be sharing the presentation?
I think you might have to ask Ahmad about that. I can provide the slides to Ahmad, and maybe he can link it to wherever he plans to host the.
Yeah, we can share the recording as well, and we'll post the slide link video.
Thank you.
Great. Okay. Yeah, I guess that's all I had. You can always email me or ping me or whatever if you have further questions. But yeah, thanks again, Ahmad, for having me here. This was a great experience.
Thank you so much for taking out time. It was really a wonderful talk.
Yeah, of course. A lot of fun.
Yeah, if we don't have any other question, I guess we can end the session here.